Okay, let's dive right into this explainer. Today, we're unraveling the invisible forces that literally shape our physical world. I mean, if you've ever felt that sudden zap of a static shock, or if you've ever just marveled at how your smartphone charges without even plugging a cable into the port, well, you've already interacted with exactly what we're talking about today. We're going to take the abstract math of the electric fields and we're going to ground it completely in real life physics. So here is our flight plan for today. We're breaking this down into 5 easy pieces. The invisible electric medium, the gravity analogy, measuring the electric field, field rules and directions, and finally, the superposition principle. Let's get into it. Starting off with section 1, the invisible electric medium. Let's look at a mystery that puzzled physicists for centuries before they finally cracked the code. I want you to think about this for a second. Have you ever held two strong magnets near each other? You can actually feel them push or pull before they even touch, right? Well, in the realm of electrical charges, it's the exact same phenomenon. If outer space is mostly just an empty void, how on earth does electric force travel through that pure emptiness to physically push or pull an object? How does an electron just sitting on your desk know that there's a positively charged ion a few inches away? It honestly feels like magic, or as Einstein famously called a similar phenomenon, spooky action at a distance. So to solve this mind-bending mystery, physicists introduced the concept of the electric field. By definition, it's a medium that transmits electric force through space. Honestly, this brilliant concept is essentially the ultimate physics hack. Instead of looking at two charges and constantly having to recalculate all these massive complex forces every single time we drop a new microscopic test charge into the mix, we just focus on the space itself. See, the source charge actually alters the space around it, creating a medium. So that second charge, it doesn't interact directly with the first charge at all. It interacts with the altered space, the field, right exactly where it's sitting. To make this invisible medium feel completely real to you, let's jump to section 2, the gravity analogy. Just as gravity acts on mass to keep your feet firmly planted on the ground, the electric field is a real, physical medium that acts on electrical charge. Look at how perfectly these two forces map onto each other. A gravitational field acts on mass, measuring force per unit mass. An electric field acts on charge, measuring force per unit charge. I mean, you don't ever question gravity, right? Because you literally feel it pulling your mass down every second. Well, the electric field is just as real. It just acts on a completely different property of matter, the electrical charge. And this right here brilliantly illustrates that these two concepts share the exact same real-life mechanics. On the top, we've got the electric field, E, which equals force divided by charge, Q, and on the bottom, gravity, G, equals force divided by mass, M. It is the exact same fundamental logic. You just take the physical force and divide it by the property it acts upon. Grasping this symmetry? That's the secret to realizing that electric fields aren't just some abstract math problem. They are a fundamental structural pillar of reality itself. All right, now that we can relate it to gravity, let's look at section 3, measuring the electric field.
You know what's really interesting here? It's how beautifully simple this rule actually is. As you can see, the electric field, represented by that vector E, is really just the electric force, F, divided by a test charge, Q. By using a standardized test charge, we get the standardized measurement across the board, which is expressed in newtons per coulomb. A newton is our unit of force, like the actual physical push or pull, and a coulomb is our unit of electrical charge.
To truly picture this in your head, we really need to understand the difference between types of fields. The electric field is a vector field. You can literally visualize this as a wind tunnel of force. A wind tunnel doesn't just have a strength. It violently pushes air in a very specific, measurable direction. Now compare that to a scalar field, like the temperature in your living room. Temperature just has a magnitude. It's, say, 72 degrees. It doesn't point north or south. But the electric field, it's always that wind tunnel. It has definitive strength, and it physically pushes in a definitive direction. So, the absolutely crucial point here is that by using this equation, we can map out this invisible wind tunnel anywhere in physical space. E equals the Coulomb constant, K, times the absolute value of the source charge, Q, divided by the distance squared, which is R squared. Basically, this means if we know how strong the source charge is, and we know exactly how far away we are measuring from it, we can calculate the exact strength of the electric wind hitting us at that specific coordinate in space. Pretty cool, right? Let's see how all this builds into the universal rules of the physical world in section 4, field rules and directions. Okay, so there are 4 indisputable laws of reality for electric fields. First, in principle, a field created by a single charge extends infinitely out into the cosmos. Second, it exists at literally every single point in space around that source. Third, its existence and strength do not depend on whether a test charge is actually there to feel it.
But the fourth point, that's the most fascinating one. A charge does not feel its own field. It's basically the physics equivalent of that old saying that you can't pull yourself up by your own bootstraps. You absolutely need an external field to create a physical force on a charge.
Now, what about the direction of our invisible wind tunnel? Well, the universal convention is to define the field's direction based on what a purely positive test charge would do. Because positive repels positive, the field lines always point directly away from positive source charges. And since positive is attracted to negative, the field lines always point directly toward negative source charges. So if you were to drop a positive test charge right into our wind tunnel, it would physically blow away from the positive sources and immediately get sucked right toward the negative ones.
But let's face it, the real world is messy, which brings us to our final application. Section 5, the superposition principle.
When you've got multiple fields overlapping in a room, you apply what's called the superposition principle. Think of it like dropping two pebbles into a pond at the same time. Those ripples overlap and combine, right? Well, in electrical physics, the total electric field at any specific point is just the vector sum of the fields from all the individual charges around it. And the beautiful part here is that each charge contributes completely independently. You totally ignore the interactions between the source charges themselves when calculating their individual contributions. You just look at what each one is doing to the space, and then simply add those effects together.
Look at how nicely this breaks down into 4 tangible, real-world steps. This completely simplifies what would otherwise be maddeningly complex electric forces. Step 1, look around your environment and identify all your source charges. Step 2, pretend the others don't even exist and calculate the field strength for each one individually. Step 3, figure out which way each specific wind tunnel is blowing. Remember, away from positive toward negative. And finally, step 4, just combine them using standard vector addition. It literally turns a seemingly impossible chaotic system into a highly predictable mechanical process.
Now, as you do those calculations, you've got to keep this ultimate sanity check in mind. Field strength always decreases as distance increases. Remember that r squared in our earlier formula? It is exactly like sitting next to a campfire on a freezing night. The closer you sit to the flames, the more intense the heat. But take just a couple steps back, and the intensity of that heat drops off dramatically. In the exact same way, the invisible electric force weakens rapidly the further you step away from your source charge. To wrap things up, I want to leave you with a truly mind-bending thought about the reality we live in, captured perfectly by this quote from our source material. When a charge moves or appears, its electric field doesn't just instantly exist everywhere in the universe at the exact same moment. It takes time. The field actually ripples out through the physical space of the universe at the ultimate cosmic speed limit, the speed of light. So get this, if a charge suddenly vanished, a test charge a light year away wouldn't even know the field was gone until a full year later. It forces us to ask a pretty profound question. Is the space around us truly just an empty void, or is it a dynamic, vibrating web of forces just waiting to be felt? Keep exploring, keep questioning, and I'll see you in the next explainer.